Hello, everyone, and welcome to our webinar Automated Workflows in Multiphysics Simulations with the Quanscient API. My name is Jukka Knutinen, and I'm the head of marketing here at Quanscient, where we have a cloud-based multiphysics simulation software called Quanscient Allsolve. At this point already, I'd like to mention that this webinar is being recorded, and all registrants will receive the timestamp recording and executive summary PDF containing all the key information. In addition, we'll be sending out the speaker slides actually already this evening. But without further ado, let's have a quick look at our agenda for today. In this little opening section, I'll give a brief introduction to our multiphysics platform, Quanscient Allsolve, and set the stage for our technical speaker of today, our Chief Product Officer and co-founder, Aser Lähdemäki. Aser will then proceed to get into the actual stake of today, which is the Quanscient API and how that can be used to, for one, solve problems currently faced with traditional APIs or design workflows in general, but to also achieve a level of automation and efficiency you can previously only have dreamed of. After presenting a real-world example from one of our customers, we'll dive into a live demo of the API, where we solve an inverse problem solution and basically demonstrate the key benefits that are the ease of use, programmatic control of simulations, and integration capabilities. After that, Aster will present the roadmap of the API development and let you in on how we involve the feedback we get from our customers in the development process, followed up by a Q&A section, and finally the conclusion and key takeaways at the end. If that sounds good to everyone, let's get right into why we're here today. So, most of you are likely already familiar with Quanscient Allsolve, but those of you who are not, let's do a quick recap. So, essentially, Allsolve is a cloud-based, FEM-based multiphysics simulation software. Now, there are plenty of multiphysics software out there, so the keywords are cloud-based. Now, what those words enable for our customers is, in a nutshell, speed, scalability, flexibility, and automation. Let's go through them one by one. So the speed is pretty self-explanatory, as you are not solving the simulations on your own hardware, but instead utilizing a next to unlimited number of CPUs in the cloud, combined with our algorithms that are built from the ground up to take advantage of this abundant computational capacity. You can reduce the runtime of large-scale simulations from literally weeks to hours and days to minutes. Now, the scalability stems from the same fact of having, again, next to unlimited capacity of computing power and RAM. So what that allows our customers to do is to basically run as many simulations as they want in parallel with zero added computational time. And with this capability, pretty much your imagination is the limit. We have had customers run 1,000 simulation Monte Carlo studies, massive parameter sweeps, manufacturer-aware design with manufacturing constraints taken into account, and more, basically resulting in better designs, increased product reliability, faster iterations, and eventually just faster product to market. Now, in terms of flexibility, there are many things actually. For one, you don't need to invest in any hardware of your own. So as you purchase a plan, all the hardware is included in addition to the software. On top of that, all physics and features are also included in every plan, so there's never a need to purchase any additional modules or anything like that. Even more, there are no user limits, which means that, again, with every plan, as many users can access the platform and projects as you want. This makes collaboration as easy as sharing a link with similar access settings than with, for example, Google Drive. What else? Well, we have the Python scripting interface. So as you set up the simulations in the GUI, a automatically generated Python script is created defining the entire setup. So basically the scripting interface is right there in the tool, and it allows our customers to modify pretty much anything they want and even add their own physics if they just know the equations. Also, regarding the flexibility, I can mention the pricing. So instead of buying licenses, you purchase a plan with a certain amount of computing power. And this computing power can be accessed by anyone in your team and only gets consumed when the simulations are running. So in essence, you're only paying for what you use. Now, the last key point was automation. And as it so happens, that's sort of the focus of this webinar. So, Without further ado, I will give the stage to our Chief Product Officer and co-founder, Aser Lähdemäki, who will walk you through the automation part through the lens of the Quanscient API. Go ahead, Aser.
Thank you. Thank you, Jukka. And hello, everyone, and thank you for joining us in this webinar today. My name is Aser Lähdemäki, and I'm the Chief Product Officer and co-founder of Quanscient. My responsibilities in Quanscient are taking care of our application and software development, except for the algorithms. And as such, I'm also deeply involved in developing and designing our public API. And today I will first discuss a little bit more in general about automation and the problems we have identified or have experience of, and then go to the live demo where I will showcase one of our white papers which we did with the API, so that you see every detail how it went. And lastly, I will present our current roadmap for the API development. So without further ado, let's start with the more generic presentation. So first of all, what is an API? Well, it's as everybody knows, application programming interface. It can be used to do integrations between softwares, automation, pipelines, and such. For example, plugins into other software, or simply automating a workflow without any manual steps. And here are a few challenges that we have found with the existing workflows. So first of all, in the existing products in the market, in many products, there is very inflexible licensing options regarding this kind of programmatic usage. So if you want to grasp all the multiphysics aspects of your design, you might need different modules per physics with different costs. And also the distribution of those licenses is restricted. And if you want to scale it in your own or cloud hardware, you need multiple licenses, and the costs can ramp up quickly. And in the existing market products, there is also limited interfacing. There are some APIs which, for example, use Java, which is starting to get a little bit old these days, not a popular choice in the scientific or engineering community anymore. There are also some Python interfaces, but their usability and clarity greatly varies. And in many cases, also you need a separate license to actually have this connectivity between softwares. And thus, it is still very common to rely on more traditional ways where you, for example, use files to communicate between software or launch the different software via command line interfaces and such. And one challenge is, of course, the local hardware. You are very much limited by it. What can you run, and how many simulations? And if you have a lot of hardware, you need to optimize its usage. If you have too little, getting more hardware can be tedious process, and also getting rid of extra hardware is not very cost effective. So what is different about Quanscient API then? Well, first of all, our licensing model is very simple. You pay for the availability of the software, and the hardware. So we give you access to certain number of cores that are always available to you. And then there is a smaller amount for the hardware usage, the actual core hours spent. But no user-based licensing, no hardware limitations except the core limit, and you can always get more. Then we have a modern API and SDK currently built with Python, but we have implemented it as a generic HTTP API, and we also have support this kind of open API definition, which means that you can generate a client for the API virtually for any language that is supported. So very wide support for different languages will be available. And the SDK package we currently have only for Python, but that is also simple to port for other languages, for example, MATLAB. And lastly, the automatic high performance computing without worrying about the hardware costs. So we do everything behind the scenes. You just choose how many nodes you want, what kind of nodes, how much RAM they have, and we do all the reservation, all the releasing, everything in the backend. Very simple for you to launch pretty large clusters with very short delays. And then let's look at a few use cases for API. First of all, as said, you can make plugins to, for example, CAD or PCB software so that you don't have to leave your familiar environment. You can make it more integrated in your design tool workflow to simulate finite element method simulations to check varying design parameters. Another use case is digital twins. For example, you could have a building automation control where you gather all the inputs, all the measured temperatures from the rooms, from outside. You know your radiator powers, you know your AC cooling, everything, and you will get live predictions through the API and can do finer control. Then, of course, power users who just like to do everything in script because there are many things that you can automate even in your like human design workflow with starting with optimization algorithms and sweeps and custom formulations and such. Then newer use cases also AI training. So as many of you may know, there are many techniques to actually do simulations with AI these days. For example, the physics-informed neural networks are a popular choice. With Quanscient, you can simulate all of your parameter space and then just use that as a training input for your model to get more quick predictions. Then automated pipelines. For example, you can do a pipeline where certain design changes get always checked by the same simulations, basically with one click or even no clicks. And then, of course, simulation data management integration. You can automate versioning and downloading, backupping your data to your own systems or different systems. Then let's go to a customer case, which is basically the automated pipeline. So we are working with Proxima Fusion, who in turn are working with Atled engineering. And Proxima Fusion is designing accelerator style fusion power plants, making the energy transformation in the future. And what they need is to simulate powerful electromagnets that are based on superconductors. And why do we need simulations? Well, if you don't simulate, you have to build prototypes. And these superconducting magnets can be very expensive. And there is a phenomena called quench, which can occur in these magnets and can even cause them to burn or even explosions. So it's very important to test them before you actually build them and run them. And a lot of variation is needed for optimal design. So here's what Proxima Fusion and Atled engineering did. On their part, they wrote all the meshing and tagging of that information, and then passing that to Quanscient API. They first estimated the degrees of freedom of the problem, then automatically selected the amount of RAM needed, and then ran first phase of simulation where they calculated the background field, and then based on that background field, which they fed to the next simulation, they ran the full fidelity coil analysis with finer mesh, and with that they got results which they were able to automatically export and put forward in the further in the post-processing pipeline. And with that, I would like to go to our live demo today. And as promised, we will be doing inverse problem solving. In this particular use case, we are trying to find some mechanical properties of our materials. And why do we want to do this? Well, as many of you for sure know, the material properties in FEM simulation can be very critical. And for example, especially if you have anisotropic materials, it can get very complex very quickly if you try to model every little detail of your design. So what you can do instead is use this kind of lumped approach where you reduce the complexity and find material parameters together for these designs. And the approach is such that we have a measurement. We have done some measurements on the device to get some idea of the behavior. And then we can formulate an inverse problem where we vary the inputs and try to find such inputs that they match the measured outputs. And that is easily done with optimization loop. And in our particular example, we will optimize PCB and some packages on the PCB material parameters for them based on measurements done in a paper by Lee et al., where we basically replicated what they did as an example of what you can do. So with that introduction, let me start the live demo. So as said, this is the original paper by Lee et al. And they made some couple of different tests where they found out the resonance frequency of this design. And in our own work, we replicated results and got pretty similar results. We did some other simplifications, which explains the variation here. So how do we do this? Well, here is Quanscient Allsolve, the main view, and I have opened the demo projects here where we have this. We published this white paper in Nordpack and prepared this demo, which is available to our users. So what I will do is take a copy of the demo. It will appear here. I have some pre-calculated results here, but we can take a look at them later. So let's rename this to sequential, just to follow it up. Okay, so just a quick intro to the basic interface. Here we have a in-browser, in-app CAD editor where you can do whole designs or just modification to imported step files or GDS files. In this case, we have recreated the whole design with this CAD editor here. Then we have some shared expressions, variables, and functions that you can define by yourself. And then, of course, the materials for the different objects. And then the physics. And here we have only considered solid mechanics, but as you can see in this list, we have a plentiful amount of different ready-made formulations via the graphical user interface, and even more via the scripting. So in this case, we have done very simple, added some clamping, and that's it. The reason why we won't need to consider this so much is that we are doing an eigenmode analysis where we let the object, we have modified the script a little bit. So if you look at here, this is the generated script. So none of this is written by hand. Everything is generated from the graphical user interface setup. But after we have enabled scripting mode here, we are free to do any modifications. And let's make it a bit larger. Here you can see that this formulation object can define your different physics. Here we only solid mechanics, inertia terms, as said. So how do we use the API then? Well, let's go back to the overview. And to use an API, you would of course need some kind of credentials. And currently we offer API keys for projects. So we can create those keys via the project info here. So let's create a key pair, and I will show how to use this in Linux environment, but we of course have Windows support too, if you need it, and Mac, of course. So we want to use environment variables so that we won't store the secret keys in our code file. So here I have opened the terminal, and I have the code project here. I will just create a simple file to store the environment variables so that I can reuse them if needed. So this file would never be shared. Like this, and then we can enable that. And then we of course need the API SDK package. And you can get that currently from us directly, and later we will have it distributed when it's fully public. So what we need to do is to copy the SDK package, and we will use a Python virtual environment. Like this, and then we activate this environment and install some dependencies, including the Allsolve SDK package. And there, now we have everything we need to run simulation API. Before we do that, let's take at the actual project files. So here we have the dependencies. We just use some matplotlib and scipy and numpy, and then of course the Allsolve SDK. And then we have our main file called optimize.py. And what we do here is we read the credentials from the environment, set up the Allsolve SDK with the credentials and correct address here. Then we have here the measured frequencies from the Lee paper. And why do we have them here is, of course, that then we have our objective function for the optimization loop. And what that basically does is start the simulation from our template, wait for until it's done, and then extract the eigen frequencies, and then calculate the residual from the computed frequencies against the measured frequencies to determine whether they are same or optimal. And what do we feed in here is a row, which is collection of the different parameters for the material. So if we, okay, yes. Let's look at this file. Yeah, here. So here we have the code to start the simulation. And first with a copy of the template, set the name for it, and then we set the simulation main script. So this is the script that actually controls the simulation formulation and such. We'll take a look at that soon. And then we select the runtime. Here I have selected just one node with the fast starting node. And here we have our parameters, which you can see are embedded in this one array. So we have the Young's modulus, shear modulus, and so forth. These four first are for the PCB itself, and then these are for the package on the PCB, as you can see, the brown ones here. And then we just start the simulation and return a handle to it so that we can follow the status and so forth. And then let's take a look at the main script here. So this file is basically just a copy of the generated script file we just saw in the UI here. So this here looks very similar, right? And then we have done some small modifications, loading the parameters that we set via the API. And then here we calculate or set up the elasticity matrix based on these several parameters that we are trying to find. And then the rest of it is setting up the formulation basically as we got from the GUI script generation. And then we have some outputs that we set here. We first of all want to output the eigenfrequencies, and then we also output the eigen or real values for the display field. So when we run this script, what will happen is that here we call the least squares from the SciPy library, and that will in turn call the objective function with each varied parameter values that we are trying to optimize. And we feed in our initial variables and then the bounds for the variables. So let's run this. Should go like this. There. You can see that it started a step of the optimization loop with these values. And when we go back to the user interface, we can see that the steps are starting to appear here and are running. And can debug the simulations from here, see the visualize the yields and so forth. And this, of course, will not look that much like the ones in the paper, as this is just from the beginning of the optimization, but something similar. And looking at the log files, we have some frequencies that are not real, and then the first actual mode is the 7th one here. So we can jump to that. And as you can see, it's you look at this cut from here, it's very similar to the first one here. So the asset differences here are due to some variation in the model and the setup. We didn't try to do as much as Lee at all, but it's pretty close, and the eigenfrequencies we get match precisely. So, and one further thing, I can show you the iteration plot. So in this plot, you can see the different trials of the shear modulus and the Young's modulus plotted against each other to show what is the optimization trying, and we can see that it's pretty much converging in here. And this was sequential, but in addition to that, you can also run runs algorithms such as evolution, where you can parallelize generation. I can show you how to do that also. So basically, it's just a different function from the SciPy, and then you create a pool of the workers, and this is not actually this is running on your machine, but it's just to control the simulations that will run in the cloud. And with this, it will start a number of simulations parallelly and test the whole space. And if we look at the convergence map, you can see that this ran for quite a while. You can see that it's trying much more widely and still converging to the same spot here as the least squares. So in this particular problem, this probably did not make much sense, but it's very useful in more complex cases. And with that, let's take a look at our future roadmap. Let me get back to the presentation. So what are we planning to do next? Currently, we are at the alpha version. We are currently working on beta version, which will bring more functionality for managing projects and simulation, checking the quota, and there will be better API key management. You will also there will also be this kind of machine user keys which can be used for more permanent installations of the keys, so that they are not connected to any person in that sense, but just your organization or a department in the organization or such. And then next year we will do our first public release, which we give a guarantee of stability. We, of course, try to keep it as stable as possible already, but there might be some changes. If there are any, we'll communicate to all of our existing API users well in advance and help them to switch to the new changes. And we also are planning to have a public repository on the OpenAPI definition so that you can create your own clients as you want. And also the Python SDK will be there so that you can suggest modifications or make a copy to another language of the SDK. Furthermore, we will also add coordinate-based picking and the meshing capability. And of course, we always improve the scaling of the platform as we go. As said, there is a huge capacity in the cloud, but of course there is some technicalities, and we work with our customers case by case on those. And if you go private cloud, then you get the most out of this, as there are some limitations that we need to do in the public cloud, but in private cloud you are free to use as much as you want. And then further down the line, there will be improved integrations and webhooks for receiving asynchronous events and such. And we are already piloting the API with several customers, as said, and now is great time to start with the API and Quanscient Allsolve and get your say in what direction we will develop this further. And the roadmap is not set in stone. We can take turns as the market needs. And with that, I would like to end my presentation. Thank you.
Thank you, Asser. for the wonderful presentation. Uh, we'll keep you here for the Q&A section. And looking at the clock, we're sort of running a bit tight, but there were actually a couple of questions already in the chat. So the first question was when we're talking about a generic HTTP API, do we mean RESTful or gRPC or something else?
Yes, so it's basically a RESTful HTTP API. We currently do not support gRPC and haven't considered it yet, at least.
And another question was that can the inverse solver estimate the damping coefficient of material?
Um, I think yes. It depends on whether you can have measurements that give you enough information for finding this coefficient, but I think it should be possible. As said, we don't have like a built-in inverse solver, but we just utilize the generic libraries available to set up these problems. So if it's possible with them, it should be possible.
Perfect. Let's take one more answer or question rather from the ones that we got beforehand. And by the way, if you still have any other questions, you can type them in the comments, and we will address them later. But for the sake of keeping in schedule, I will ask that will the API be compatible with future versions of Quanscient Allsolve, and how will updates be managed? You sort of touched on that
Yes,
a little bit in the roadmap, but could you perhaps expand on that slightly?
yes, of course. So as said, we will do our first public release next year. And what public release means here is that we will give some guarantee of its stability further in the future. And there will be a notice well in advance if there is a next generation of the API or any backward incompatibilities. Of course, we will avoid them as much as we can. So I would say I cannot give you any timeline right now, but we will give you a timeline when we do the public release about how long do we promise that it's stable.
All right. Now, looks like we're just in time to wrap things up with the key takeaways. So at this point, I'd like to thank Asser once again for the wonderful presentation, and of course, all of you guys for the awesome questions. So, what did we see here today? Well, in the beginning, I introduced you to Quanscient Allsolve, which is a cloud-based multiphysics simulation software. And four key benefits were presented, which were speed, scalability, flexibility, and automation. And the speed is basically reducing the runtime from weeks to hours and days to minutes. Scalability is the ability to run as many simulations in parallel as you like with zero added computational time, enabling sweeps and optimization studies, etc. Flexibility is the Python scripting interface, enabling basically unlimited customization, the unlimited number of users with every plan, the hardware and all the features being included in every plan, and the pricing structure to make sure you only pay for what you use. Then, automation, the focus of today's session, is the ability to programmatically control simulations, develop proprietary design workflows, and eventually plug into your CAD software directly, and to overall remove lengthy manual setups and repetitive tasks, all the while running more simulations faster with more accurate results. Now, if what you heard here today sounds like something you'd like to explore, I warmly invite you to get in touch with us. The most direct way is to head to the URL shown on the screen and simply schedule a 30-minute appointment with our CRO, Mr. Nicolas Stra. Nicola will sit down with you and any of your colleagues to just explore how Quanscient also could fit your use cases and existing workflows. So basically give you a good idea of what working with also might look like, what kind of problems it could solve, and most importantly, what kind of possibilities it might open for you. So again, to schedule the session, simply head to the URL visible on the screen now. With that, I'd like to thank you all for participating in this webinar with us and wish you all a great rest of the day. Thank you and take care.